And first of all, we'll revise what the proportion is, what odds are, and then we'll talk about z-tests to compare proportions, 2 by 2 table. We'll talk about chi-square tests, and then we'll look at some common epidemiologic measures, but we will not talk about logistic regression. That's an error in the outline. Okay, so logistic regression we will talk about later in the course. So can somebody tell us what the proportion is? It's more than likely that you have seen this slide before many years ago, maybe like 4 weeks ago in the beginning of the class, but what's the proportion? And can you give us an example of a proportion?
Part of a whole expressed in percentage.
Part of a whole expressed in percentages. So give an example of a proportion in real life.
Okay, so let's say in our sample we have a sample, we have measured systolic blood pressure,
Okay.
and we want to check, even though we know that a normal systolic pressure could be between 120 to 140 millimeters per mercury.
Yeah.
We want to check proportion of those that are proportion of the sample subjects that are maybe at above 130 millimeters per mercury. So if we have 100 in our sample, and say 30 of the people have systolic blood pressure above 130, that will be 30 divided by 100. So a proportion of 30%.
Yeah.
That's my guess. That's my guess.
That's very good. Any other examples? Yes.
Okay. Maybe proportion of males in this class.
Proportion of nurses in this class. Very good. Yep. Anyone else has an example? So we've seen proportion of people who have hypertension, proportion of nurses in this class. Okay. So proportions are everywhere in nature, right?
They are what, sir?
So they are everywhere in nature, right? Many of us already intuitively know what the proportion is before I even talked about it here today, even if you don't know that what you actually know is the proportion. Okay, so that's really important to know that proportions are not strange. Every time we're thinking about something as a part of a whole, right, then we're thinking about proportions, and we'll talk about proportions a lot today. One measure that is somewhat related to proportions is odds. Now, odds, on the other hand, require a little bit of understanding. Okay, they're not necessarily intuitive. Where a proportion is, because it's a fraction, it ranges from 0 to 1. You cannot have a proportion that is negative, and you cannot have a proportion that is greater than 1. But sometimes we want to express the proportion in a different way, and so we recalculate it in a way and then call it odds. But really what we're looking at in the odds is that we're looking at the likelihood that something is happening versus the likelihood that it does not happen, right? Occurrence divided by non-occurrence. Those are odds. And odds are really, really useful in decision making. If you're trying to decide whether, if I run every day, every morning, I run every morning, what is the odds of hypertension, right? Am I likely to have hypertension? One of the questions that you're thinking about is what's the odds of hypertension in people who run versus the odds of not having hypertension in people who run. And so if the odds of hypertension are higher when you run, then you say that, oh, I don't think I should be running because running makes the odds higher. Okay. So we're intuitively thinking about it, but we might not call it odds. And one place where odds are commonly used, commonly mentioned, and many of us and people who gamble will have already come across odds very often. So odds, that's a language that's very commonly used among people who gamble because it helps to make decisions. So all of this to set the stage, because we're going to use these words throughout the next hour or so. And I suspect that we will need to go past the hour. There's another intuition that I would like for you to know is that a lot of statistics is based on the normal distribution. A lot of statistics assumes that the variable that we're dealing with is continuous. But proportion is not continuous. And so to be able to get the proportion into a continuous mode, statisticians have done some work. And Bernoulli realized that if you toss a coin, every time you toss a coin, it can either be odds or tail. And that means that the odds of heads is 0.5. Or sorry, the proportion is 0.5. The chance that a person will have heads, given that there's two options, it's 1 divided by 2 is 0.5, assuming that there is a fair coin. And if you then repeat, you throw this coin up multiple times with the proportion being 0.5, and if you throw it 10 times, you will likely find a scenario where sometimes it's head, sometimes it's not head. And so based on that, you can draw a normal distribution of the probabilities that you get. Okay. And essentially this distribution allows us to go from what is ordinarily a non-continuous data that cannot be normally distributed to a continuous data that can be normally distributed, which then allows us to subject our statistics to the proportion. Okay. And because then we have a distribution that is somewhat normal, because we have repeated the coin toss multiple times, we can make some we can do some statistics, like I said. This distribution where something can either be yes or no, can either be heads or tail, there's two potential outcomes. But when you repeat it multiple times, you then get something that can approximate the normal distribution. This is called the binomial distribution. And this binomial distribution then allows us to have the z-test. We'll talk about it today. It allows us to do some additional analysis that you will come across when we're talking about regression. Okay. So the key intuition that I want you to just bear in mind is two things. First of all, we have the proportion, which is a part of something, a part of a whole, and there's only two possible outcomes. But when we have something that can only be two possible outcomes, but we repeat it multiple times, we can come up with the probabilities that then looks like a normal distribution. And those probabilities are based on a binomial distribution. So all of this is the statistics that underlies the z-test. It allows us to be able to determine when somebody gives you a proportion, you want to decide whether that proportion is different from another proportion. To do that, you need the z-test, and the z-test is based on the binomial distribution. If you don't remember all of this, remember that the z-test is what we use to compare proportions. And last week we talked about t-tests for one sample distribution, for one sample t-test, where you're comparing one mean to a standard mean. Here in z-test, we can also do the same thing. We can compare one proportion to a standard proportion. And maybe that standard might be a reference, and we'll take a number of examples to illustrate this point. In much the same way, we can obtain a p-value, and we can also use the confidence interval. So let me take an example, and maybe it can help you understand what we're trying to do here. 56% of 45 neonates with intestinal obstruction who were operated at your center died within 30 days post-op. You learned that only 30% of neonates operated for the same condition at the National Center of Excellence died in the same time frame. Okay, there's 45 neonates, 56% of them died. 56% died in your center. But when you compare that to the National Center of Excellence, only 30% died in that center. And you want to compare this 30% and this 56%. You want to check if your performance is much different from theirs. And the way to do that, because you have two proportions, 56% or 0.56 and 30% or 0.3, the way to do that is z-test. And if you plug in the numbers into this formula, this p hat is the estimated proportion from your own sample, which is the 56%. And this p is the reference proportion. Okay, this is the reference proportion. And so you can subtract, and this, you can subtract this from that and multiply, find the square root, you get a value of 3.806. This value of 3.806, you look at it in the z table, the p-value is 0.001. Another way to conduct the z-test is to use the 95% confidence interval. Okay. And for this 95% confidence interval, basically, we will calculate the p hat plus or minus 1.96. Plus or minus here, essentially, we're doing is p minus 1.96 times this p hat, 1 minus p hat divided by n, and then p plus 1.96, because remember that the confidence interval is a range. And so our values go from 0.56 to, we calculate this when we plug in numbers. Ultimately, the final value is 0.415 to 0.705. And so we can compare this 0.415 and to 0.705 to the 30%. Okay, and compared to 30%, we operated for the same condition. And here, what we note is that 30% is not within this range. 30% is not within this range. And we therefore conclude that the National Center of Excellence, the 30% from the National Center of Excellence, is significantly different from the 56% from your own center. Any questions? Yes, Jerry.
So yeah, so my question is this. I noticed that for the t-test, we only had the confidence interval just to tell us the range where our mean value falls, or the range, the allowance, plus or minus, based on maybe standard error or standard deviation. But you are saying now that in the z-test, we are actually comparing the known proportion to check if it is contained within the confidence interval of our own sample proportion, right?
So that's not completely true. So in the t-test as well, you can check whether that mean, the reference mean, lies within this confidence interval. You can do that as well. Okay.
Yeah.
All right. So that's the one sample. And as we go on, I'm going to complicate it a little bit more. So I want you to understand it very well before we move on to the next slide. Any questions? Is it completely clear to you?
Sorry, sir. So in the range of confusion, so like when we did the one sample t-test,
Yes.
we compared it to a known mean. Say, for instance, the mean systolic blood pressure is supposed to be 120.
Yeah.
Right? And then we had a sample. We now compared. We had a sample of people who were hypertensive, and then we compared. We measured their systolic blood pressure after an intervention, and of course, it did like a difference in the mean, and we had a systolic blood pressure of 128 with a confidence interval of 122 to 129.
Yeah.
Now, from what we learned, the interpretation would be that the mean systolic blood pressure in that group was 128, but with a confidence interval of a lower confidence of 122 to 129, such to say. Sorry. I didn't catch any point where we tend to say that the mean systolic blood pressure was significant because the standard of 120 was contained interval about sample mean. I don't know if you understand what I'm saying.
I understand what you're saying. Yeah. So it's an omission from last week, right? When we have the one sample tests, we can either obtain the p-value like I have done in first step, or we can obtain a confidence interval and determine whether that confidence interval contains the reference or the standard that we're comparing to. That's an acceptable way as well. Okay. All right. Thank you. So next, any other questions? Can I get thumbs up indicating that you all perfectly understand this one sample Z test? Okay, I see some hands, 7 people, 8, 9, okay. Okay, all right, thank you. So that's the one sample Z. This formula that I've shown you for the confidence interval, it's a rough approach. If you had to choose between one approach or the other, if you're most comfortable with the p-value, go ahead with the p-value, that's fine. But this formula for the confidence interval is rough. And I'll show you another formula, and I'll show you one reason why you have to tread carefully when you're using the confidence interval approach. Okay? All right, so let's look at this example. At Kinondoni Hospital, there were 24 deaths of women in labor. 24 deaths of women in labor or in the postpartum period out of 1,200 deliveries. So what is the proportion of deaths? Can somebody tell us quickly? Or just walk us through how you will obtain it.
24 over 1,200.
24 over 1,200. Okay, good. Does anybody else in the class agree or disagree?
I agree.
Agree? Okay. All right. Thank you. So 24 over 1,200. So we want to compare this proportion, this estimate, to a comparable national estimate, 0.8%. Okay? So they're saying that at Kinondoni Hospital, the proportion is 0.02, which is 2%. But nationally, the deaths that you're seeing, that proportion is 0.8%. Do you think that, somebody asked, do you think that this 0.8% is different from the 2%? In that case, we can use the Z test. And this is this a one sample Z test? Does everybody agree that this is a one sample Z test, and why? Okay. So Jerry, okay, all right. So this is a one sample Z test. We have one sample and we're comparing to a reference. And here as well, we can obtain the p-value by walking through this calculation. We can also use this Wald formula, which is the rough Wald formula for confidence interval. Can somebody interpret the p-value and interpret the confidence interval approach? Anyone wants to try?
Okay, let me try.
Yes.
So based on the p-value, then there would be a significant difference in the findings from the Kinondoni Hospital as opposed to the national estimate. However, based on the confidence interval, now that reference, this national estimate is 0.8%, it does fall within the 0.4 to 3.6% confidence interval. Therefore, it would make it appear as if the finding is there's no significant difference.
Yes.
So there's a conflict between what the p-value is showing and what the confidence interval is showing.
Excellent. Thank you. So, and that's why I said that this confidence interval approach is a rough approach. Basically, what we've done here is you see this value that we're using to obtain the standard error for the confidence interval. In this case, we've sort of used a shortcut. This shortcut makes sense. It's intuitive. It's how we understand it. It comes directly from the t-test. It's easy to understand. But here, in proportions, because proportions, we're dealing with a different kind of measure. Whenever we have a rare condition where something is not happening as frequently, right? Maybe the proportion is less than 10%, for instance, or 5%, depending on who you ask. This rough Wald formula, it's not called rough Wald, I'm the one who calls it rough so that you can understand. But this Wald formula for obtaining the confidence interval, it breaks down. This p-value continues to be correct. It's the confidence interval that breaks down. Therefore, we have to use another approach instead. And this other approach that we're going to use instead is the Wilson score formula. This slide is not in your notes. It's not in the one that you might have downloaded, because I just updated some of these slides. So I'll share this slide once we're done. So in this case, we need to use a different confidence interval because the condition is rare. I mean, you might just say, why don't you just use the p-value approach? And that's always correct. That's fine. But if you use this Wilson score formula, you get a different set of confidence intervals. And this Wilson score formula is what we want to use whenever the n is small, right? Instead of 1200, maybe it's 43 or 19. When the p is near 0 or 1, so in this case, the p we have 0.8%, right? Or maybe if we had gotten something like 99% instead, or just whenever you're not sure, you should use the Wilson score formula. So this Wilson score formula is more complicated. As you can see, there's so much more going on in this case. But now we obtain a confidence interval whose values are consistent with what we obtained with the p-value. I like this confidence interval approach because it could layer up to some other things, some other assessments and measures that we're going to do later. When we start talking about effect modification, this intuition of comparing a confidence interval to something else will come to play. And that's why we're continuing to show it to you. Okay, so the p-value works, the confidence interval works, but you have to use the right formula. You can use the Wald formula if you're just trying to get a rough estimate, and if these other criteria are met. Okay. Now, that's one sample z-test. Any questions about it?
So, sir,
yep.
You're saying that when we do a z-test for a sample and we have, just to be sure whether we should go further to do a Wilson score test, do we have to maybe check for both the p-values and the Wald's test for that sample. And if there is a conflict, we go further to do the Wilson test, because I don't think we can know whether the p-value and the confidence interval may be conflicting at the stage of the Wald's test.
Yeah, very good question. So one way to know which one to do is actually this table, is what this table is showing you. If you have a small sample, 25 people, small samples, usually we say less than 30. If you have a small sample, if you have a proportion that is near 0 or 1, i.e. maybe 0.8, 0.5%, and 0.8 is 0.008, right? And 0.5, 0.005, or 95% is 0.95, all of which is also extreme proportions. Then you don't actually have to do the Wald first. You can immediately know that you should be using the Wilson score formula. Also, I should remind you that all of this, you're going to do it in the software. You're not going to do it by hand. And so in SPSS, for instance, you might just need to tick Wald or Wilson score, or you can ask it to present all of it, and you can look at the values and you see if the p-value approach is consistent with the Wald or consistent with the Wilson. So essentially what we're trying to do here is for you to understand what is happening, because ultimately you're not going to calculate by hand most of the time anyway. Even though the calculation is straightforward, you can do this in 5 minutes. But most times you would do it in software. But it's just for you to know when to use what. So you're not expected to first of all calculate the Wald. Instead, you should use the decision rules. Is it a small sample, or is it an extreme p-value, extreme proportion? That's it. Is it a small sample, or is it an extreme proportion? Or if you're completely unsure, then you should just use the Wilson score formula. Okay. All right. Any other questions? Okay, so we're now going to talk about the.
No way, you can. Okay.
We're now going to talk about the two sample proportion. And now I see that this slide is blank, and that's surprising to me. But basically what we're doing in the two sample proportion, you remember that when we did t-test, we also said that you can actually look at two samples and you can compare proportions in two samples, and you would use another formula. And I'm going to share my full screen instead for this because it's not showing you the formula. Let's see. Maybe it will show it. Right, this formula. Okay, so we can use this formula, and we will have one proportion and the other proportion that we're comparing. And we will also have to calculate the proportion in the full population. Okay, so let me take that again. Sometimes we want to compare two proportions. Ideally, these should be independent proportions. And so that means in the context of like randomized trials, you have two study arms or study groups. One group gets treatment A, another group gets treatment B. And you calculate the proportion of those who experience the outcome in group A and those who experience the outcome in group B. And you're comparing both groups. Okay? In that scenario, you can use the z-test. The z-tests of two proportions, which is the standard z-test.
Sorry, sir, say again.
When you're comparing one proportion to another proportion, and that both proportions are from independent samples, such as when you're conducting a randomized trial, you have a randomized trial, you're testing treatment A versus treatment B. Let's say you have two antihypertensive drugs. One group gets lisinopril, another group gets maybe more diuretic or something like that. And you're comparing both groups. You're looking at the blood pressure after 6 weeks in both groups. You want to see whether how many people have hypertension in group A, how many people have hypertension in group B. So you have two proportions. If you want to compare these two proportions, you can use the Z test. Okay. Now let's take this example. In a phase 3 trial of a new drug to treat multiple sclerosis, 33% of 488 patients in treatment arm A had a confirmed disability progression. Confirmed disability progression is the outcome, compared to 39% of 244 patients in placebo arm. Okay, was the new drug more efficacious than placebo? So the first thing you'll do is that you'll calculate the proportion in treatment in group A or in the treatment group, and that is 33%. You calculate the proportion in the placebo group, and that is 39%. And then you subject that to this formula. It doesn't matter which one you call P1 or P2. So if you put this in front, then that means you have negative, which you can find an absolute value. If you put this at the back, then you will need the negative sign, but ultimately you will calculate a Z statistic. And in this case, you have the Z statistic of 6.952. If you read that from the p-value table, from the Z table, you get a p-value less than 0.001. This is the Z test for comparing two sample proportions, which is the standard Z test. Any questions? And this is fairly straightforward. As you can see, you have two groups, you calculate, and here this P is the proportion in the overall sample, right? While this is proportion in group A and this is proportion in group B. It's just math, right? You know the formula, plug in the numbers, and you get the value at the end of the table. And this
so
day,
is the proportion in the whole sample?
That's this P. Yes, that's
proportion in. Okay.
So everybody who had the outcome, so in this case will be 33% of 48 plus 39% of 244. Whatever that number is, you use that to get. In this case, that proportion is 0.35 in the entire study. That's
sorry, sir, I'm a little confused. So that means, just help me out to calculate the proportion in the whole population.
Yeah.
The whole sample, we will get what the number for the number that represents 33% of 488.
Yes.
And then we get the number that represents 39 of 224.
Yes.
Add them together, that becomes our numerator.
Yes.
Then we add 488 plus 244, that's our denominator.
Exactly.
And calculate the proportion of that.
Correct. And if you do that in this case, you get 0.35. Okay, excellent. And this is another example. A malaria vaccine trial among 2,000 children reports 12% malaria incidence among the vaccinated, 18% among the unvaccinated after 1 year. Okay? Assume that 1,000 children have received vaccination, 1,000 did not, right? Which is not a surprising design in the trial. What was the incidence of malaria significantly lower among vaccinated children? So you need to determine what your P1 is, 12%, what your P2 is, 18%, or like I said, it doesn't matter which one is 1 or 2. And then you need to determine what your P is, P hat in this case, which is 15%. You add those together, 15%. And then you plug this into the formula, you get a Z statistic of 235, which is a very large Z statistic, which is definitely less than 0.001. Okay?
So I'm confused.
Okay. Now,
I'm confused.
here's what we have.
2000.
You should try to walk through this question.
Huh?
You should try to walk through this question. Let's see. What's your P hat? 1. What's your P1?
That's the thing. I'm seeing 2,000 children and 12% reported.
Yes.
This 12% will be of the 2,000.
No. So if you have a trial, that means you have 2 study groups. You have 2 arms.
Okay.
One arm in one arm you had 1,000 children. In the second arm you had 1,000 children.
No.
Okay.
Oh, okay. Okay.
You get it now. So
Yes, I do.
that's 1,000 plus 1,000, how you got 2,000, which is the denominator for the P. So that's how we get 15% for the proportion, which is literally just 12% and 18%, the average of both, because the ends are the same, right? Because the ends are the same. Any questions? Any other question? I think Yusuf has his hand up.
Yes, thank you. When you said these 2 sample Z test is actually the standardized Z test, is that the reason why we are actually not bothered about the confidence interval when it comes to these 2 sample Z tests? Because we were actually combining both the p-value and the confidence interval for the 1 sample Z test. Is it that for the 2?
So, very excellent question. So for this as well, you can use the confidence interval, but I have not shown that approach. So if you use the confidence interval, you will obtain 2 confidence intervals and look to see if the 2 confidence intervals don't overlap. Okay, but like you said, we might not need to bother with it because we have the p-value approach, which is straightforward, and we can just move forward with that. But if you wanted to do that, you will have to construct the confidence interval for each of the proportions and then compare the confidence intervals for both. So it's a bit more work, it's more involving, unlike for the 1 sample t-test approach where you can clearly see, you're comparing one value to the confidence interval. It's more straightforward.
But if we do it with the software, is it that we are not going to get confidence interval for it, but we display for it too?
No, so if you do it with the software, I don't remember. It depends on how you actually call. I don't use SPSS often, but I suspect that you should be able to get the confidence interval for an SPSS for both. Yes.
Sorry,
Debbie.
Doc.
Yeah.
Okay, sorry. Debbie can go.
Okay.
Okay, I just wanted to know if the actual value, the numerical value of the Z statistic has any significance at all, or is it just something that is going to yield a p-value? Is there anything we can interpret from that number?
How do I say this? The numerical value of the Z statistic, you cannot by itself make any sense of it without knowing another measure called the degrees of freedom. Right? When you have a 2x2 table, the degrees of freedom is 1. And if you know the degrees of freedom and the Z statistic, you can find the p-value. By itself, however, the Z statistic might not be interpretable Like you cannot say, oh, the Z statistic is this, therefore this is that, right? So that's not something that you can do. It's more like a value that's the value that's actually being calculated in the back end, but which you cannot translate. Now, this is different from when we say the Z-score. For instance, when we're dealing with, in pediatrics, for instance, we're dealing with like height for age Z-score, weight for age Z-score. That's not the same exact thing.
You know, I know those two things are completely different.
Yeah.
Thank you.
Okay.
Okay.
Yeah.
So,
Jerry?
Doc,
Yeah.
can I go on?
Yes, please.
Can I say, just correct me if I'm wrong, can I say that whether it's a one sample t-test or a one sample z-test, since we are comparing our sample mean with a known value, that the best matrix for assessing whether the differences in mean is significant would be checking if the known mean is contained within the confidence interval of the sample mean. Is that correct?
Yes, that's correct.
Okay, so when we are now doing two samples, because we are comparing one against another, then even if there is a physically visual difference between the means, I mean, from what the example you are projecting now, 12% of the 1,000 children that were vaccinated had, sorry, the report shows that 12% malaria incidence in those vaccinated and 18% among those unvaccinated. By just looking at this visually, we can already tell that there is a 6% difference. So though there is a 6% difference between those that were vaccinated against those that were not vaccinated. But for us to check whether this difference is significant within the individual data points, we would have to use a p-value to check the level of significance. Am I correct?
That's correct. But you can also use confidence interval, which is the point that I think Yusuf was getting to earlier.
Okay.
Right? You can construct the confidence interval around this 12% because it's a sample estimate. And you can also construct a confidence interval around this 18% and then compare both. But it's the confidence intervals that you will compare.
Okay, so if the percentage of children with malaria in the unvaccinated, if it is contained within the confidence interval of the vaccinated children.
If the confidence intervals overlap.
Okay.
Right?
Oh, overlap.
And yes. So if one confidence interval goes from, so for the 12%, if the confidence interval goes from 10 to 14, and for the 18%, the confidence interval goes from 16 to 20, those confidence intervals do not overlap. Right? But if one confidence interval overlaps with the second one, say for instance for the 12%, you have confidence interval going from 8 to 16. And for the second one, you have confidence interval going from 14 to 22. Those confidence intervals overlap. Okay? But you know, the issue that you have.
Your network was breaking.
Oh, the example I was giving is that if the confidence interval for 12% goes from 8 to 16, and the confidence interval for 18% goes from 14 to 22, those confidence intervals overlap. Right?
Sorry, doctor, I'm so sorry. Sorry, doctor, I'm so sorry to bring you back. My internet, I didn't get you at all. When you say overlap, you said if the confidence interval for the 12% is 10 to maybe 16, and then the confidence interval for the 18 is maybe 14 to 20, they overlap, right?
Yeah. Wait, I'm going to.
So that means
best to right, so you can see. Can you see my screen? My
okay.
Blank.
Yeah, yes, sir.
Okay.
Yes, sir. Yes, sir.
Okay, so if you have 12% and you have 18%, right? And this confidence interval goes from 10 to 14, while this one goes from 16 to 20, right? There's no overlap. There's space here.
Yes, sir. Yes, sir.
But if you have a confidence interval that goes from 8 to 16, and you have a confidence interval that goes from 14 to 22, there's overlap. So in this case, because these confidence intervals are overlapping, you cannot say that they are different. But the point that I was making is you have to construct these confidence intervals and look at the amount of work that it takes to construct one confidence interval for just one sample. Then now you're going to do it in 2 steps. And if you run into errors, then, but the intuition is there that it's the confidence intervals that you have to compare. And the reason you're comparing the confidence intervals is because these are samples. This is not the population value. I remember that we said the sample is subject to error. So that's why you cannot use the raw value. You have to use the confidence interval. Okay. All right. So long discussion that we had. And so I'm going to go back to sharing this screen so we can. Okay. So long discussion that we had. And so the key takeaway really is, when should you use the z-test? And you want to use the z-test when the proportions, when you're trying to figure out whether the proportions differ from one another and when the groups are independent. That's when you want to use the z-test. Okay. All right. So the next thing we want to talk about is chi-square. And it looks like we're now at 6 minutes to the end of the hour. So we spent a lot of time on z-test. We spent time on ANOVA and then z-test. I don't think we have enough time for chi-square. And chi-square is involving by itself. And then I was going to also talk about common epidemiologic measures. That's at least another hour of discussion. So I wonder if we should take a break here and call it a day, because we will not be able to, even if we're going to say, okay, let's do this in 30 minutes, we will not be able to finish it in 30 minutes. So maybe we should take a break and then we can try to continue this next week.